So this lecture is also working with the NIST atomic spectral database. There's some things in those tables that we may not understand, and some things on the Grotrian diagrams that we may not understand. So there's atoms are pretty complicated if you think about it. They've got a lot of electrons. The electrons are interacting with each other. The electrons are in orbits. So even though the orbits don't look like planetary orbits, we can still think of it that way in terms of today's lecture. And so we'll get into how the spin of the electron couples with the spin of the orbital. So the orbital angular momentum quantum number is actually the quantum number for the angular momentum in the orbital. And then you have the electron with angular momentum. And so those can be with each other or against each other. And so we'll figure out how to keep track of all of those things. And so we keep track of those with term symbols. So in the atomic spectral database, if we put in mercury, 400 to 800 nanometers and hit go, we get the Grotrian diagram, we get the table of lines, we see the spectrum here. These spectral lines are giving all of the, 5 different spectral lines, giving us what appears to our eye as white light. And so in graduate school, I was, I don't remember what year, probably my 3rd or 4th year, I noticed a bunch of like cardboard box stuff thrown in the trash outside of one of the professor's offices. And so here I'm dumpster diving, right? So I said, "What's all this?" And he said, "Well, I tried to make this spectrometer to go on the overhead projector." So I don't know if you remember overhead projectors. You ever seen those? It's like a little box with a light inside and a little thing. And he wanted to make it to where it would send a rainbow on the screen, like from the light bulb. And he couldn't get the slits to work out and everything, so he just got angry and threw the whole thing in the trash. And I looked and I saw this little piece of plastic on his deal. That's a diffraction grating. And so I was like, ding! And I stuck it on this Cheez-It box that I had in the windowsill, okay, and made a spectrometer out of it. So I cut the corner out of this here, and you can aim it at the lights, and you can see all 5 of these lines. And so here you go. So you have to aim that corner at the light and look through there. Do you see? Just move it up and down until you see the lines. Yeah. So that's my Cheez-It spectrometer. You see it? Yeah, you see all 5 of them. So it's pretty fun. Little 50-cent piece of plastic that's scratched to the very precise manner. So you have to have the lines equally spaced, and they have to be the right spacing apart to interact with visible light and get good dispersion. Okay, but pretty much any scratched up plastic will work, but it won't give you a beautiful rainbow dispersion. You can buy these diffraction glasses and things like that now. We have a bunch. We're just really not in school in the summer. I mean, there is summer school, but the Chem Club and everything doesn't really do much in the summer. But I've always wanted to get these fireworks glasses, because you can buy them from American Paper Optics and put your logos and everything on the side. We did it one year when I was president of the Rotary Club. And then you go to pass them out at the fireworks display, and it's got diffraction lines on the plastic crisscrossed 4 different ways. And so every point of light becomes 8 different rainbows. And it's really incredible. The cool thing about fireworks is those are atomic spectra. And so it's not a continuum. It's just like this. So like if there was mercury in one of those fireworks, you would see those 5 points of light burst out. And it's so cool. And you tilt your head and you see them like spin around the points of light. So we passed out these glasses to everybody in the community. And then I was just having a blast watching the fireworks explode and everybody go, "Oh, wow." As they tilt and watch the rainbows. Once you figure out, oh, that makes it look cool, then everybody, you do it. You can't help not do it. So these are the spectral lines for mercury. Here's the Grotrian diagram. And over here's the table that you get from the NIST atomic spectral database. We understand electron configurations. That's what we've been doing for the last couple of days. The wavelength is the transition wavelength. So you can say it with me all together. We won't have to pause. So a transition is a difference in energy levels. Okay, so these are the 2 electron configurations for the 2 energy levels that are being connected. Okay, the intensity, where do they think the intensity comes from? That's the transition dipole moment integral. Okay, so we know what that column's from. But here's this term symbol column. And so that's the term of the upper state and the term of the lower state. And buried inside the term symbols are these J quantum numbers. So we have Ji and Jk. And then we have the G's. Those are the degeneracies. So we have, we've seen that in the Boltzmann distribution. So how cool is that? We have every column in this table from NIST, the Atomic Spectral Database, that we've talked about in this class, except for term symbols. And so that's today. We're going to talk about term symbols. We saw them on the Grotrian diagram for helium. So the simplest multi-electron atom, helium, just has 2 electrons. And with 2 electrons, you need to start keeping track of these angular momentum couplings. Spin-orbit coupling, they call it. And so those are across the top. Let's zoom in on helium. Notice we have 2 identical electron configurations. And so how do we tell the difference between those? And that is how the spins of the electrons in those orbits, they can be spin paired or spin unpaired, like we talked about last time. And whether they're paired or unpaired will give us different total angular momentum. And so that's why we have these different term symbols associated with those 2 electron configurations. So term symbols help us distinguish between these identical electron configurations. We're using these terms. This word actually has a statistical meaning. So let me think. Like a Venn diagram, you have a configuration, might be a certain circle in that configuration, and then there's lots of little things inside that circle, which we would call permutations. So does everybody understand the difference between a configuration and a permutation? A permutation is an individual instance that has that kind of configuration. Now, how might we understand this? Well, think about this. Let's look at boron, just the p orbitals in boron. It's got 3 p orbitals. I could put an electron in the first orbital, or I could put an electron in the second orbital, or I could put an electron in the third orbital. But notice how all of those are 2p1. So these are 3 permutations of the 2p1 configuration. Does that make sense now? Yeah, so this little instance here might be this one. This little instance here might be this one. And this little instance right here might be this top one. But all of those are the 2p1 configuration. So now you understand the difference between a configuration and a permutation. Now, some of the books get in there and actually have you draw the little arrows, the up and down arrows, and try to figure out all the permutations, add those up, and get the configuration, okay? I never liked doing it that way because I never knew if I got all the pictures. Now, for boron, it's pretty easy. We have these 3, and then we can have the spin down. So there's 6, right? There's only 6 ways to put an electron in 3p orbitals. 3 spin ups, 3 spin downs, we've got all 6. But when you get into like carbon, where you have 2 electrons, they could be all, this one and that one and that one, this one, down and that one, then flip the spins, and pretty soon it gets confusing trying to draw these little arrows. There's not a systematic way of drawing your pictures, but there is a systematic way of coming up with all of the couplings of angular momentum. So I'm going to teach you that systematic way so that you always get all of the answers and you don't have to think about all the little pictures. The danger in that is you don't have a a connection to the orbitals, like the pictures. You know, it's nice to kind of see the pictures. Oh, I've got a spin up electron in this m sub l equals -1 orbital. But the benefit of learning the Clebsch-Gordon series, which we'll talk about, is that you know you got all of the possibilities. So these mathematical sets, and that's what we're going to be dealing with, the curly brackets means a mathematical set of numbers. They deal with only the electrons in unfilled shells, unfilled subshells. So like for the boron example, the 1s2 is filled, the 2s2 is filled. So the only thing we would deal with for boron is just that one electron in an unfilled subshell. So we're only concerned about how that electron that's free to flip, how it interacts with the orbitals that it's in. So it's only those orbitals that have some freedom associated with them, the unfilled subshells. All the others, there's no freedom on how to make it a 1s2. You have one orbital, 2 electrons in it. That's the only answer you could get. So we just ignore all of the orbitals that are fixed and subshells that are fixed and filled, and we deal with the unfilled subshells. So then the term symbols for all those ground state atoms with filled subshells are singlet S0, singlet S0. So you can know that. So for, you know, all of the group 2, those are 2s2 orbitals. Those are filled subshells. So those are going to be the ground state, singlet S0, noble gases, the zinc group, so the D10 group. And so all of those that have fully filled subshells are going to be singlet S0, these terms that we're dealing with. So that's the term symbol right there. And so let's talk about this Clebsch-Gordon series. Name Clebsch, that is a lot of consonants. Okay. It must be from Fayette County. Okay, my wife's from Fayette County, and there's a lot of names like that. There'll be like 3 syllables and only 1 vowel, and I always look at it and go, how does that work? So anyway, these are the pieces of the term symbol. There's 3 parts to it. There's the total angular momentum part, and again, just to remind you, we're only looking at electrons and unfilled subshells. And so here's how we come up with the L term. Over here in this little flow chart, they're calling this the electrostatic term, but it's the total angular momentum, total orbital angular momentum. So the orbital part is a big piece. And these are the little L's are the L for each electron. And so we couple them 2 at a time. Now, this can get really, really long and tedious if you had 3 electrons and 4 electrons, because you combine the first 2 and come up with the capital L, and then you take all of those capital L's and combine them with the 3rd electron. So you expand the set, and then you take that set of L's and combine it with the 4th electron and keep going. So the worst one that I could think of would be the chromium one, because it pulls an electron from 4s, and so we have 4s1, that's an unpaired electron, and then a 3d5. So we have 6 unpaired electrons, and you would do it pairwise. You would do the first 2, create a set of capital L's, then add the second, or add the third, and create a set of L's, then add the 4th, the 5th, the 6th, and it would just be a nested problem that would take pages and pages. I figure I'm just going to teach you 2. We're just going to couple 2 electrons, or just 1. Sometimes we can just pick 1 and see what the terms are for 1. So we'll start with 1 electron, then we'll go to 2 electrons, and then that's all we need to do. Once you figure that out, then you could continue the thing on. So this is how we combine the little L's for 2 electrons. And think about what we're doing. We have this orbital has angular momentum in it. And so you could kind of think about, let's think about, here's the sun, okay? And Earth is rotating around the sun, okay? Not to scale, right? And so Earth is rotating around the sun, and that's spinning around the sun. So that's a huge angular momentum piece. And then the Earth has two options, right? It can spin this way, or it could spin the other way. You see how one adds to the angular momentum? So if you remember the right-hand rule from physics, you have the path, you have the rotation, and the thumb is the angular momentum vector. Okay, so the Earth's going this direction, it's spinning that direction, so there's an angular momentum vector going up. What if the Earth is spinning the other direction? It's going this direction, then the angular momentum is going down. And then if it's orbiting the sun, it's got an angular momentum vector going up. So we've got an angular momentum vector going up, and if it's spinning with that same direction, it has its angular momentum vector on top. So that angular momentum vector is longer. If it's spinning against its orbit, it goes down against it, and so that total vector is shorter. So that's what we mean by spin-orbit coupling, the spin of the electrons coupling with the orbit. Now, we know the orbits are like a wave function, but the thinking is correct. We have an angular momentum vector, and then the tiny little angular momentum vector on the electron can go with it or against it. And so how do we keep track of this vector and that one adding to it or going down? The Clebsch-Gordon series. So we have a maximum value and a minimum value, and then because the electron is spin 1/2, then the difference between it going up and going down is 1, right? It's plus 1/2, minus 1/2. You add those two together because the difference of it being up or down is 1. And so that's where this 1 comes from. So we start with the max, and that would be the orbit and the electron spinning in the same direction. So that's the max length of the vector. And then we go down and find the min. And so they could be against each other. And then we have -1 between the max and the min until we fill out the whole set. And so let's say the max, let's just say the max is 5 and the min is 2, then it's 5, 4, 3, 2. So that's the full set. Does that make sense? You find the max, you find the min, and then you drop down an integer from max to min and fill out the whole set. So in those curly brackets, that's a set of values for the capital L. Okay, erase these because I think it's going to need that space. Okay, so then we have the multiplicity. This is the spin correlation plus the electrostatic piece. And so that's net spin of the electrons. We're going to be adding that up. And so this S, again, has a max and min with -1 in between. This is typically, plus 1/2 and plus 1/2, all the way down to plus 1/2, minus 1/2. So I know that typically the students are confused by why we start with plus 1/2. What if it's going down, right? Well, this series is taking into account all the possibilities of spin up and spin down. So you don't have to worry about it. Just assume that they're all pointing in the same direction for the first pair. They're against each other in the last pair. This will give you the spread of possible spins. And then the total angular momentum quantum number, that J value, is where you then add in the L plus the S. And so this is how the spin quantum number is interacting with the orbital quantum number. So we have the numbers from our set, L plus S down to L minus S. And you do this one for each L and for each S. Let's see, yeah. So this is really a nested part of the problem. If we had 3 L's in our set, for each L, we would add in S and subtract S. And then you go to the next L and do this set. And then you do the next L and do this set. So this problem does nest out a little bit, even with just 2 electrons. So let's do some examples. This is just the scheme of how we come up with those sets. But there's 3 sets. There's the L set, the S set, and the J set. And the J is nested, meaning for every L you have a J, a series of J values. And this is how we write out those terms. You see this down here, this triplet P2, triplet P1, triplet P0. Okay, so that's, here's all the quantum numbers. That multiplicity is up here in the as a prefix superscript. Then you have the capital L piece, and then you have the set of J values. So whenever you pick an L, you come up with the J values. Then you have 3 different terms if you have 3 J values. Now let's do some examples. So here, let's just do the terms for sodium. So this is the ground state electron configuration. We have 1 unpaired electron, so we're only interested in that S1 electron. Now, this will be overly simple since we only have 1 electron. So the sets are all going to contain just one value, right? Because we don't have L1 plus L2. There's no max, there's no min, it's just L. And so the capital L's have capital letters, just like when we had the lowercase L's, you can write on the side. Lowercase L's could be, 0, 1, 2, 3, all the way up to n minus 1. That was our L values. And we gave those letters, little s, little p, little d, little f, etc. Okay. When we get to capital L's, we have, capital letters or uppercase. But we use the same scheme for giving us the capital or uppercase letters. These are lowercase. So when we make those terms, we use the same kind of SPDF labeling, but they're with uppercase letters. So then it's bad enough we have all these letters. Now they're case sensitive. Science is a mess. I mean, there's just too many things you have to give letters and terms to. Okay, so this works, and you can guess that now. Like if you have a single electron in an s orbital, the term's going to be a capital S. If we had a single electron in the g orbital, let's say a really excited state sodium, that'd be a capital G for that term. So whatever orbital a single electron is in, that's going to be the term for that particular situation. Okay, so then let's calculate S. It's, again, we don't have S1 plus S2 because we just have a single electron, and it's plus 1/2 because that's the spin of our electron. And so we do 2S plus 1, so 2 times 1/2 plus 1 is 2. That's a doublet. So we have a number here that's associated with the multiplicity, but we give it a term, singlet, doublet, triplet, quartet, quintet, I guess. That's as high as I've ever seen. Maybe there's sextets and octets and so on, septets. Now we do the total angular momentum quantum number where we add in L plus S and L minus S. So we calculate the minimum first. So we have 0 here and 1/2 there. So this is going to be, 1/2. And then we get down here to 0 minus 1/2. And then these 2 little things right here are really important. This is absolute value. So we don't ever have negative numbers. Okay. So that would be minus 1/2 inside the absolute value term. So that's going to equal plus 1/2. So it ends up being the max and the min are equal in this situation. And so we just have one J value, which would be 1/2. So J is equal to 1/2. So we have L, we have the multiplicity, and we have the J value. So we know the term, there's only one. It's a doublet S 1/2. So that's how we would label that ground state energy in the NIST atomic spectral database, is that level would have the electron configuration of neon 3s1, And then the term symbol for that level would be doublet S 1/2. Okay. So this is the same also for any NS1 configuration. So if it was in the 4S, the 5S, the 6S, it'd be the same. And if it's not sodium, what if it's lithium, potassium, any of those that just have one electron in an S orbital? This is the same term. So I guess I want you to be comfortable with this shorthand here, right? Notice how this is now general to any atom and any ion. Let's say we had magnesium +1. It's lost its second electron, so now it's NS1. And so that ion is, that configuration is going to have several terms associated. This would be one of those terms, the NS1. Any NS1 configuration is going to have this term symbol. Okay, let's do the excited state sodium atom. So let's have the sodium atom with that electron excited to some p orbital. And I went ahead and used that designation, NP1, because I don't really care if it's a 4p, a 5p, a 6p, a 7p. I just have one electron excited to some p orbital. And that allows me in that Grotrian diagram, remember the columns had a term symbol at the top associated with them. So that whole column was all of the NP1 energies. And that they're sort of grouped. They're grouped by term symbols. And so that column would be this term symbol here. Okay, so the electron's in a p orbital. So the term is a capital P. So that's straightforward. We only have an L1 because we don't have a second electron. Same thing for S. It's still a 1/2. And so we have a doublet. And then we couple L and S. And so now we have 1 plus a half. Okay. So they typically write these in terms of halves. 3 halves. Okay. And 1 minus a half, okay, is going to be, so it'd be 1/2. Brain freeze. And again, it's going to be positive. So those are our 2 J levels. We have 2 of them. How do I know there aren't any integers in between? Well, think about it. If I take 3 halves, this next term would be 3 halves minus 2 halves, which is equal to 1/2. And that is equal to the minimum. So you still subtract 1 as you go down until you reach the minimum. And if you reach the minimum in the second term, then you just have 2 terms. So here's our 2 J values. And so we have 2 terms in this situation, a doublet P 3 halves and a doublet P 1/2. So when the sodium electron moves up to a p orbital, there's 2 p orbital. So in the Grotrian diagram, we would look and we would see in that column of the doublet p column, we would see all of the NP energies. But if we zoomed in on the 3p1, the neon 3p1, if we zoomed in on that orbital, we would see that there's 2 little orbitals there very close together. And one of those would be the doublet P 3 halves, and the other would be the doublet P 1/2. And so we're talking about this really tiny hyperfine splitting. So we have a dramatic difference in the electron configuration. What are the electron configurations? It would be the neon core 3p1, and then a huge energy jump, neon core 4p1, neon core 5p1. So those are huge differences in energy level. We zoom in, and then we see these tiny little differences between the doublet P 3 halves and the doublet P 1/2. And so that's going to be the same for any NP1 configuration. And so this is what we see in spectroscopy. We see the ground state, the doublet S 1/2, and then if we zoomed in to that electron configuration, we would see this splitting, and it's a really tiny splitting. It's only 17 wave numbers. Compute that over into nanometers, and it's a 0.6 nanometer difference. And so that sodium line, if we zoom in on it, is a doublet, really. Well, let's see. I thought I had a picture of it. So in the spectrum, we would see this line that was huge, bright line. But if we zoomed in on it and looked at it carefully, so I'm zooming in, okay, we would see this. We'd see that it's a doublet, and we could resolve that hyperfine splitting. 0.6 wave number difference, or 0.6 nanometer difference. And this spectrometer can see it, the little Cheez-It spectrometer, but you have to have a lot of sodium in your lights. And I'm kind of sad that the mercury lights used to be contaminated with sodium, and then we could see it in class, and they've gotten better. So there's very little sodium in the mercury lights anymore, so you really can't see it. But if you were to take this out at night and find a sodium lamp, you could see the doublet if you squeeze down the slits. And so by pinching this box corner, you reduce the amount of light that comes through, but you improve your resolution. So if anybody wants to come do that, look and see, you can change the resolution of the spectrometer by pinching the slits down. And you see how the lines sharpen up, but they also get dimmer. Can you see? You pinch it too much, it all goes away. So somewhere between pinching them closed and just narrowing them, you can improve your resolution. So what you're seeing in that is individual little terms in the mercury spectrum, which is pretty complicated. So here's the lowest energy term symbols for S, P, and D. The F ones are just ridiculously complicated. Look how bad the D ones get. Any of the S1 electron configurations, those are going to be doublet S, and then there's going to be the J values, like 3/2, 1/2, okay? Or, just 1/2 for this doublet S, but then for the P, it was doublet P, 3/2 and 1/2. That fits for the P1, like we just did for sodium in P1, but it also fits for the P5. So over there, the halogens, they are 3p5, 4p5, and so on. And think about the halogens. Instead of, you've got, let me just show you. For the p5, okay, you've got filling those up with 5 electrons. You've got an unpaired electron in a single orbital, and you can put it here, you can put it there, you can put it there. You have the same statistics, and so you're going to have the same term symbol, the same J values, and everything. So, the P2s and P4s are the same, and then the P3s are kind of unique. These are all of the different L values and multiplicities that you can get. And down here, these D4s and D6s, there's just lots of ways to couple these 4 electrons together. So, you even get up to some I terms here. So that's pretty crazy. Singlet I, or here's a doublet I, and there's a G and an H, and so on. We're not going to do those. I don't have the patience to do those. But you start with just that D4 electron configuration, and these are all the permutations of how you can put those arrows, spin up, spin down, and coupling in the M sub L quantum numbers. So this small table gives you the permutations within the ground state electron configuration. So remember, the configuration is the big Venn diagram circle, and then all the little pieces in between, different ways to put the arrows in, is the permutations. The Clebsch-Gordon series gives these plus all the excited state terms. And so this is just the ground state terms. We get all the excited state terms from the Clebsch-Gordon series too. Okay. So let's practice now. Let's do carbon. So it's the helium core, 2s2, NP2. So it could be 2p2, 3p2, 4p2, 5p2, etc. So now that we have 2 electrons, it actually becomes interesting. So you you add the two orbitals together, so p plus p. So what is p? So sp, so that's L equals 1. So everybody see how I did that? Always remember the s orbital is a sphere, that's also 0. So I start out sp, so p, the L equals 1. So this is going to be 1 plus 1, and that's the max value. 1 minus 1 is the min value. So this is going to go from 2 down to 0. So how do I fill out this table from 2 down to 0? Well, I subtract 1 for the next one. So 2 minus 1 is 1, and then 1 minus 1 is 0. So I'm going to have 3 L values. So the max is 2, the min is 0, 2, 1, 0, and then so that's DPS. Okay, so I go SPD, I get up to 2, I know it's a D, SP, and S. So those are the three orbitals. It seems silly to do the fist thing for S, P, and D. Okay, you're probably thinking, oh, he's crazy. But when you get to G and H and all of that, it's like S, P, D, F, G. So I know for G, L equals 4. Okay, so that's when it really becomes useful. Okay, so then the S. So let's figure out the spin. So where do we get 1? Well, we have 1/2 plus 1/2 down to 1/2 minus 1/2. So the max is 1 and the min is 0. So when S equals 1, 2S plus 1 is 3. That's a triplet. So the triplet corresponds to that one. And then when S equals 0, you have 2 times 0 plus 1 is 1. So that's a singlet. So when S is equal to 0, it's a singlet. When S is equal to 1, that's a triplet. So that's the first two series, the L series and the S series. Now for each of the L's, this is when you see the nested part. We're going to start with the D term and calculate all of the J's. And then we do the P term and calculate all of the J's for that. And then the S term and calculate all the J's. So these are the sort of main terms that we have: triplet D, triplet P, triplet S, singlet D, singlet P, singlet S. And then we can calculate the J values next. Okay, looks like you got them all. So now the total angular momentum quantum number for the triplet D, and this is something that you need to know. Like if you didn't have this information, and I gave you triplet D, you need to be able to say, okay, for D, it's SPD, I know L equals 2. And for triplet, I know S equals 1. So you've got to be able to interpret this. You've got to be able to look at triplet D and know L is 2. And you got to look at the triplet piece and know that S is 1. Don't mess up and say it's 3. It's not 3, it's 1. So the L, it's L plus S. So L is here, S is here. So the maximum is 3, the minimum is 1, and so we have one term in between. So 3, 2, 1 is our J values for the triplet D. Then we do the next one in the series, singlet D. So again, for D, L equals 2. For a singlet, S equals 0. And whether 2 is a plus 0 or a minus 0, it's still just 2. So we only have one term for this, and so that would be a singlet D2 would be the energy levels for that term. Then for the triplet P, so when we have a p orbital, that means L equals 1. And when we have a triplet, that means S equals 1. So for our series, we have L plus S and down to L minus S. So we get 2, 1, 0 for our J values for this particular series. You see how it's not hard, it's just tedious. You're making up all these little series, and you just got to keep track of which one you're working on. Okay, and then for singlet P orbital means that L equals 1. Singlet means that S equals 0. And again, plus or minus 0, we just have one J value for the singlet P. And you're going to notice, what do we think triplet and singlet mean? Like, why do we call them triplet and singlet? Notice the triplets all have 3 energy levels, and the singlets all have 1. So that's where this word triplet and singlet come from. It's related to how many energy levels you're going to have. Okay. And then for the sodium, we had that doublet P, 3 halves, 1 half. So the doublet had 2 energy levels, had 2 J values. For triplet S, and that doesn't work for the S, but it works for the others. So we have triplet S, but it still only ends up with one J value. So S, L equals 0. The triplet means S equals 1. So 0 plus 1. And here the absolute value pays off. 0 minus 1 is a minus 1, but we take the absolute value, so it's plus 1. And so there's nothing in between those. I see this on the exam every time, people getting negative J values and messing up. Okay. And so then for the singlet S, S is 0, singlet is, let's see, I said that the angular momentum S means L is 0, the singlet means that S is 0, and again, we have a single term there. So these are all of the terms for carbon. Triplet D, 3, 2, 1, singlet D2, triplet P, 2, 1, 0, singlet P1, triplet S1, and singlet S0. Here's the thing that you can kind of check your work on. What is the L for D? SPD, 2, okay? Notice how these 3 levels are centered on 2. So it's up 1, 0, and down 1. So you take that orbital angular momentum and you add in the J's, it goes up 1 and down 1 and is centered on that D. Same thing for P. What is L for P? It's 1. And so then it goes up 1 and down 1 from that. So those 3 levels are centered on the capital L for that particular term. It's just something that you can observe. Okay. Anything I can clarify or questions you like, is this something I see or a trend that you want to talk about?
How do you know when it's supposed to be lowercase and when it's supposed to be uppercase?
Good question. So an individual electron in an individual orbital, that's when we would use the lowercase. Okay, so back, I got a lot of animations here, but we go back to that part in the notes here. So see, this is a little L right there. So one of these little L's here, those would be the lowercase, SPDF. And when we write out our electron configurations, we use lowercase, like 1s2, 2s2, 2p6, etc. Those are the lowercase L's because they're talking about, I guess, individual orbitals. We're coupling them together to kind of take, like, think about our solar system, the angular momentum of our solar system. We used to have 9 planets, now 8, right? And so we would have all of those L's added together, and each individual planet would be a little L. But if we added Mars and Earth together, then that would be a capital L. And so that's when we go to the uppercase letters. When we start making these series, then we're using the uppercase letters. I apologize for this, that there's an S, capital S, sort of quantum number for calculating the net spin, and there's also a capital S term. So that's a little uncomfortable. Like in the same calculation, you've got 2 uses for capital S. I don't know what else to do. I mean, this is not my doing, not my fault, as they say. This is just the scientists that worked on this, and then we've never decided to bite the bullet and change that. So let's look then at the levels table for the NIST Atomic Spectral Database. So this little table here that said the term symbols for the ground state electron configurations for P2 only showed these three. It didn't show the triplet S, it didn't show the triplet D, and it didn't show the singlet P. So that seems strange. It seems like we've contradicted ourselves, because look at all these terms. Okay. But what it showed, this little table is for the ground state electron configuration. So that would be the ground state for carbon would be 1s2, 2s2, 2p2. So the n equals 2 for the ground state. But what if I put one of those electrons in the 3p? It's still a np2. Okay, one's in the 2p, one's in the 3p, and that's when we get these other terms. And so here's all of the possibilities for these terms, and we see the ground state when it's 2p2. We have those three terms, the triplet P, the singlet D, and the singlet S. But when we allow that electron to go up to the 2p, 3p, and so on, we get all these others. Those are still P2 systems. It's just that one electron is in a different shell than the other. But that allows us to have some decoupling of the electrons when we're not violating the Pauli exclusion principle. Like, what would be a violation of the Pauli exclusion principle in the ground state that's not in the excited state? Remember, those three p orbitals are degenerate because they have an m sub L equal -1, 0, and 1. Okay? I cannot do this. I cannot put two spin-up electrons in the same m sub L. So we can't do that. Okay? But I can, if this is the m sub L for the 2p, and this is the m sub L for the 3p. So what I can't do in the ground state, I can do in the excited state. I can have a spin-up electron in the m sub L -1 in the 2p subshell and in the 3p subshell. It can also be in the m-1 orbital. And so that allows me to have more terms. And that's what's going on with some of these, triplet P and so on. Okay. So the Clebsch-Gordon series produces all of the permutations for the ground state and the excited state. So it gives you everything. And that's nice. Okay. So only one ground state. This is the ground state, but there's a ground state electron configuration that contains all of them. Okay. And this is it. This is the Russell-Saunders coupling scheme. There's also a JJ coupling scheme. We're just learning one of the two. Okay. We're almost done. All right. Thank y'all.